Today I will present our recent work, and it's a joint work with Huang from Indiana University. So first thing first, let's talk about some background information. So zero-knowledge proof allow a prover to convince a verifier that the prover holds some secret witness, fulfill some relation, and without revealing this secret witness. And in this work, we'll use the circuit representation of the relation. And we focus on two additional properties of the zero-knowledge proof of knowledge. So the first one is succinctness. So it just means the fast verifier and short proof. So we actually have two definitions here: weak one, a strong one. So the weak one means that the time and the proof size is sublinear in the number of gates or the size of circuits, and the strong one means additionally sublinear in the length of the witness. And the next property is transparentness. So it means that the proof does not require a previously trust setup. So we examine the setup transparent ZK proofs. So the first group of protocol is MPC-in-the-Head based ones, such as the KKW and Limbo. So thanks to the MPC-in-the-Head, so they straightforwardly support arbitrary finite fields. But the problem is that you really require linear verify time and linear communication. That's not succinctness. So on the other hand, we have the ZK protocol based on the GKR protocol, which provide weak succinctness, and especially the protocol Virgo and the Virgo++ use the low degree test to make the GKR procedure fully zero knowledge, and additionally provide a strong succinctness. But they also inherit the constraints through the low degree test, the constraint on the choices of the fields. And Virgo and Virgo++, they use the square or missing prime fields, and they will not work very well for example, on binary fields. And they need to simulate the binary field operations on their field, and which can be very costly. So our work is motivated by this question. So it is possible to construct a concretely efficient zero-knowledge proof system that can easily support computation on arbitrary fields, arbitrary finite fields. So the exploration use the Dubhe protocol. So the protocol only have a weak succinctness, but we can argue that it is still very useful for concrete applications, especially with a small size of witness. In that case, Dubhe usually have a much better result than the protocol with strong succinctness like the Virgo and Virgo++, because their witness commitment scheme is very costly. And Dubhe easily work for computation over any fields, and compare with the existing MPC-in-the-Head based ZK knowledge proof. Dubhe protocols are both asymptotically and concretely more efficient. And we apply the approach to develop a number of applications, such as the identification and the signature scheme, and the ring identification and ring signature. And all of these schemes are based on the standard and modified version of AES. So let's look at what's our observation and Dubhe's goal. So we'll compare some building blocks on this 5 aspects: the zero knowledge, or the performance of verifier and proof, and the support of two kind of gates, the linear gates and nonlinear gates. So we are starting from the KKW protocol, which is the MPC-in-the-Head based one zero knowledge proof. So it has almost free support for the linear gates. But the costly part is the nonlinear gates. So they need to prove the linear gates, such as multiplication. So they need additional run to generate multiplication triples, and use the cut and choose scheme to prove that, and resulting in a linear verifier and a linear proof size, so which is not very good. And our primary objective is to minimize the presence of the nonlinear gates, and ultimately aiming to eliminate all the nonlinear gates, so that we can use the best part of the KKW protocol. So the first solution is to use the GKR protocol. So this protocol is restricted on structured circuits. So for example, a circuit with D layers, and each layer has M number of gates. So the GKR protocol provides the D time log M of verifier and the D time log M of proof size. And it can reduce the number of nonlinear gates for the verifier to check to a mere number of D but with the trade-off of introducing d log m additional rounds. And the second solution is use fully linear probabilistically checkable proof, the FLPCP. So this one with actual 1 or 2 rounds can verify a number of multiplications in linear time and with a square root of proof size. But the verifier only needs to check the linear relations. So with these 3 building blocks, the Dubhe tries to combine them in some way and for the best of all the 3 worlds. So let's look at the more detailed view of how we combine these 3 building blocks together. So we assume we are starting from a computation with D layer, and each layer has m polynomial gates. So we can view the GKR and FLPCP as transformation that guarantee the equivalence of computational correctness. So we first apply the GKR transform, so it can transform the d time m polynomial gates into that's big of d time log m linear gates, and with big of d polynomial gates. And additionally, we will have d of log m number of witnesses. And then we apply the FLPCP transform targeting the big of d polynomial gates and transform that to the linear gates. And with additionally number of big of d witnesses. So after these 2 transform, we are living with a circuit that only has linear operations. So we can directly apply the plug in the KKW, the simplified KKW that only deal with linear gates, and then that finish our proof system. So for the application, so let's look at a proof of the AES. So we examined the AES circuit and found that the only nonlinear operations in the AES circuit is the special inverse in the sub-byte step. So by special inverse, we mean that for an input that is non-zero, the output is just the normal inverse of that one, and also a special case where the input is 0, then the output should also be 0. So previous protocols that want to prove AES, they like Bankit and Limbo, their approach is just use a modified version of AES. So they require that all the inputs to the sub-byte should be non-zero. So the consequences to that, the first one is the key space is shrinked. And also, we are not clear whether this slightly modified AES is still secure or not. So our aim, we'll do is try to do with the unmodified version of AES, and we provide you 2 different approaches. So the first one is with some actual witness. We just take the output of the special inverse as an additional actual witness, and we convert these special inverse relations equivalent into 2 symmetric polynomial relations. So the a time ab plus 1 equals 0 and b time ba plus 1 equals 0. So this polynomial is 2 arrays with a total degree of 3, very easy to prove. But the drawback of this approach is that the computation and the communication will grow linearly as the number of AES blocks. So that means in the scenario when we need to prove multiple blocks, such as a counter model AES, so the performance will not scale up very well. So we'll provide you a second approach. So it's without actual witness. So we just directly treat the sub-bytes as 8 table lookups, and each has 256 entries. And we encode these tables and 8 arrays polynomial and use the technique we talked before to prove that. So we'll compare these 2 approaches on the experiments over the counter model AES. So both approaches have a linear probe time, and the actual witness-based prover runs more than 100 faster than the other one, but the proof size is also larger on the when the block size is much larger. So this shows a trade-off between the prover time and the proof size. And this is also one of the cases that the Limbo's approach does not work, because it is just not possible to guarantee that all the sub-bytes, all the inputs to the sub-bytes and to the out of the blocks, AES has non-zero inputs, so that is not possible. So one directly use of the proof of AES is the identification and signature schemes. So identification scheme is an interactive protocol that allows the prover to prove his identity to a verifier who knows the public key of the prover. And a signature scheme is a non-interactive protocol, or we can use the finite transform to concrete that. And they share the same keygen step, it's just the encryption of AES using AES, and they have similar proof. So it's just a proof of that encryption. But the signature scheme has additionally requirement that the message you want to sign is provided as a query to the random oracle to provide the initial randoms. So we use the AES with actual witness as a circuit to prove these two schemes. And but the GKR part is skipped for the non-interactive signature to save the number of runs and to have better performance. So we have this performance of identification schemes and compare with, we have better results than Quicksilver and Virgo and Virgo++, and have a similar result with Limbo. And for signature scheme with 128-bit comparison, computational security. So Virgo and the Virgo++ have a large number here because, as I said before, they are not good at dealing with binary circuits. And Limbo here, we have a little increase of number than Limbo. And because that Limbo has dealing with a modified version of AES, and we have competitive results compared with hash-based schemes like the Sphinx. And then another application is ring identification and ring signature. So ring identification allows to prove in zero knowledge that one's identity belongs to a predefined group, and the ring signature means that the signed message on behalf of a group without revealing the signer's identity. So they are just the proof of these two relations. So using AES encryption to get an ID and prove that ID belongs to some group of ID. And to prove the membership, we can just transform that relation into a series of multiplication and use the circuit of multiplication tree to prove that. And this signature shows the identification performance, very fast prover verifier and small proof size. And for signature, we compare our scheme with our protocol with KKW. And for ring size smaller than 8,000, we outperform theirs. And so this concludes my talk. So we invite you to read our paper in detail if you are interested and play with our implementation open source at this link. Thank you.